Hello, everybody, and welcome back to the second session today, the final session of this year's maths tutorials exam questions from paper 2 in the Leaving Cert exam, which will be delivered by Paul Sheehan.
Thank you, Eamon, for the introduction. My name, folks, is Paul Sheehan. I'm a tutor with the CEIA, and I have been so since 2017 timeframe. And I've given previous lectures on trigonometry and on algebra. And so just before I continue, I'm just a little, the environment and where I'm in at the moment, I have to wear a mask. So I'm just a little self-conscious about it. So I'll turn off the camera if you don't mind. Rest assured, it will be me. In terms of the agenda today, so I'll go through a question on probability, combinations, a circle, coordinate geometry, trigonometry and geometry, financial mathematics, length, area, and volume. If there's time, I'll do a question on statistics and functions. So these are taken from recent years' sample papers. So the sample papers that are distributed for the pre-papers, for the pre-exams at the end of February timeframe. So that's ultimately where a lot of these questions come from. You may recognize some of them, you might not recognize others. So without further ado, we might as well just start straight into it. So the method by which I want to present today is, I have a whiteboard. Here. All right, Eamon, can you let me know if you can see the whiteboard? So
I can, sorry to interrupt you there, Paul. I can see the whiteboard fine. I'm just wondering, when the PowerPoint is up, maybe
yes,
it might be it's not on full screen, or it's not on the presentation one.
All right, right. So anyway, this is the real start of the presentation. Everything up to this point was preamble. So the question 1, right? In a quiz, students are asked to solve 2 logic puzzles, and 45% of the students solved problem 1. 25% of the students solved both problems. What is the probability that a student solved the second problem, given that the student had already solved the first problem? So just an issue that I've encountered before, and I almost fell into it myself. This kind of full stop here is unfortunately placed. I in my haste originally, I interpreted this as 1.25%. It's not. It's 1 full stop, and then the next sentence is 25% of the students solve both problems. So that's just a note on format. This is a question on conditional probability. Okay. So if I often think it's very important in these questions just to lay out first your notation. All right. So if I go to the desktop, all right. So what I would say is that sure. So the probability of 1 is the probability of solving the first puzzle. Okay, the probability of 2 is the probability of solving the second problem. So the second puzzle, okay? So the probability that a student solve the second problem, given that they had already solved the first problem. So basically, if this was represented as a Venn diagram, what you have is something like this, okay? And this is a set of all the people who solved the first problem, and this is a set of all the people who solved the second problem. So the question says, the probability that a student solved the second puzzle, given that they had already solved the first problem. So what you're doing, the line given that they had already solved the first problem, is that represents this entire shaded area here. Okay, that's all the people who had solved puzzle 1. Okay, The question says the probability that the student solved the second problem, given that they'd already solved the first problem. So what you're looking for then is this area. Okay, you'll be basically asked what fraction of the overall region 1 is this particular red area. Okay, the probability that the student had solved problem 2, given that they had already solved problem 1. Okay, so that is the probability of 2 given 1. That's it expressed in a normal notation. And the formula for that is the probability of 2 intersection 1 all over the probability of 1. Okay, now we know from the question, I go back to the question, 25% of the students solved both problems. Okay, so therefore this is 0.25 in the numerator. And 45% of the students solved problem 1. So therefore this probability of 1 is 0.45. Okay, and therefore that is 0.25 divided by 0.45, which is 5/9. So therefore the probability that students solve the second puzzle, given that they had already solved the first puzzle, is 5/9. All right. So that's conditional probability. Conditional probability. Okay. The second problem in that question, it's unrelated. The probability of a water pump being faulty is 0.04. A random sample of 12 pumps is selected off the production line. Calculate the probability that I, only one pump is faulty, correct to 2 decimal places, and 2, no more than 3 pumps are faulty, correct to 2 decimal places. So let's take the very first part there. Only one pump is faulty, correct to 2 decimal places. So I'll just clear the canvas. So if you have difficulty, if you are choosing to write this down, and perhaps if you lose some information when I erase the whiteboard, just remember, of course, it is on YouTube, so it's all backed up. So again, what I like to do in these questions is I like to write down just a notation, okay? So the probability of a pump being faulty, the probability of being faulty, that is 0.04, we're given it. Therefore, the probability of it not being faulty, all right, that equals, well, it's 0.04. Well, the probability, so it's either faulty or it's not, okay? So the probability of being faulty plus the probability of it not being faulty is 1. So therefore, the probability of it not being faulty is 1 minus the probability of it being faulty. Okay, therefore, the probability that it's not faulty, 1 minus 0.04, and that equals 0.96. Okay, so the probability that, as per the question, a random sample of 12 pumps is selected off the production line. Okay, calculate the probability that only one pump is faulty, correct 2 decimal places. So the probability that only one pump is faulty, one pump is faulty. Okay, now any one of the 12 pumps can be faulty. Okay, so it's 12 choose 1. Okay, so any one of those 12 can be faulty. And then so we do this. This is the Bernoulli trials, right? So what we do is we multiply that by 0.04 to the power of 1, because one of those 12 must be faulty, and all the other 11 must be not faulty. Okay, so it's a direct application there of the formula. And if you were to work that out, that tumbles down to 0.31. Okay, so that's the probability that only one pump is faulty, correct 2 decimal places. So the next question is calculate the probability that no more than 3 pumps are faulty, correct to 2 decimal places. So the English here is often very important in these particular questions. Okay, when he says that the probability that no more than 3 pumps are faulty. So what we're no more than 3 pumps are faulty. So what that allows the probability that 0 pumps are faulty. Okay, 0 pumps are faulty. Okay, plus the probability that 1 pump is faulty. Okay, plus the probability that 2 pumps are faulty. Plus the probability that 3 pumps are faulty. Okay. So we've accounted for all the different scenarios that are covered by the phrase no more than 3 pumps are faulty. So we can't go to 4 pumps are faulty, for example, because he says the probability that no more than 3 pumps are faulty. And the concept of no more than 3 pumps are being faulty is made up of 0 pumps are faulty, plus the probability that 1 pump is faulty, plus the probability that 2 pumps are faulty, plus the probability of 3 pumps are faulty. And these are mutually exclusive events. So we can't have 0 pumps are faulty and 1 pump is faulty at the same time. So we add the individual probabilities. Okay. So again, the determining the probability, each of these 4 probabilities is again an application of the Bernoulli trials. So how many ways do we have of selecting 0 pumps out of 12? And the probability of a faulty pump to the power of 0 by the probability of a non-faulty pump to the power of 12. Okay. And then the number of ways of selecting 1 pump from 12 where that pump is faulty, and all the remaining 11 pumps are not faulty. And then the number of ways of choosing 2 pumps from 12, and where those 2 pumps are faulty, and all the remaining 10 pumps are not faulty. And then finally, the number of ways of choosing 3 from 12 pumps, where those 3 pumps are faulty, and the remaining 9 pumps are not faulty. Okay, so what you do is you add all them up as per the plus signs here, and that comes out to 99.90%. So that is a probability that no more than 3 pumps are faulty. Okay. So, question 2 again is, in the same area of combinatorics. I think that's that's kind of the grandiose term for this area of the course. So he has here, if 15 choose r plus 3 is equal to 15 choose 4r minus 13, find r given that r plus 3 is not equal to 4r minus 13. Okay. So, so we have 15 choose r plus 3 all over, sorry, 15 choose r plus 3, that equals 15 choose 4r minus 13. Okay, and r equals question mark. So this notation, so you might recall from the book, this is in general terms. So the n choose r equals n choose n minus r. Sorry, moving there between capitals and non-capitals. Sorry. So just to be sure, there, get capital R on that side. So hence the 15 choose r plus 3. Okay, that is equal to, that can be rewritten as 15 choose 15 minus r plus 3. Okay, and that is equal to 15 12 minus r. Okay, so therefore we can say, if we can rewrite in the very first line, we can say 15 choose 12 minus r equals 15 choose 4r minus 13. Okay, therefore we can equate the lower parts. We can say that 12 minus r equals 4r minus 13, and therefore or what is it? 5 or equals 25, or equals 5. Okay. So again, that's just kind of, it's quite abstract. Okay, but it's just a kind of direct application of this particular behavior or identity, right? The next question, this is probably a little more interesting. It's probably a little more real world. So a bag contains 5 yellow, 3 green, 6 blue, and 2 black discs. If 4 discs are chosen at random, find the probability that all the discs are the same color. Okay, so we'll just leave it at that for the moment. So all the discs are the same color. All right. So what color can they be? If all 4 discs are to be the same color, they're either all 4 of them are yellow or all 4 of them are blue. There aren't enough green ones and there aren't enough black ones. Okay. So I go back to the whiteboard. So again, I always like just to write down. So there's 5 yellow. Sorry, 5 yellow. Okay, and 3 green. Right, and 6 blue. And 2 black. Okay, so the probability that all discs are the same color. So the probability that all discs okay, so as I said already, they can be all 4 can be yellow, or all 4 can be blue. Okay, so all 4 can't be yellow and all 4 can't be blue at the same time. So they're mutually exclusive events. So we add their, their probabilities. So so if the 4 are yellow, well then it's 5 choose 4. We're choosing 4 yellow discs from the 5 yellow discs, or the number of combinations can be choosing the 4 blue discs from the 6 blue discs in total, and the number of ways of choosing 4 blue from 6 blue is that, right? And all over, so either these combinations are acceptable, 5 choose 4 or 6 choose 4. Okay, all over the total number of ways of choosing 4 things from 16 discs. Okay, and the total number of ways of choosing 4 things from 16 things is 16 choose 4. Okay, so if you were to work that out in your calculator, you would get 1 over 91. So the probability of picking out at random all 4 of the same, that would be 1 over 91. It's a 9 there. Okay. So the next question is, all discs are different colors. Okay. So all discs are different colors. So what that means is that we've 1 yellow, we've 1 green, we've 1 blue, and we've 1 black. So in other words, that's what we want. 1 yellow, 1 green, 1 blue, 1 black. So so that is kind of one specific condition that we want. We want 1 yellow, and we want 1 green, and we want 1 blue, and we want 1 black. Okay, so how do we get, so we want 1 yellow out of the 5 yellows. So the number of ways of choosing 1 yellow from those of the, hello? Eamon?
Hello?
Yeah, hello. There was just a little chirp there from my machine.
Oh. Okay. Oh yeah, it says something.
I just wondering, were you trying to communicate with me?
No. I'm not sure. It's a glitch in the internet or something.
All right. So the number of ways of choosing 5 of choosing 1 yellow disk from 5 yellow disks, and the number of ways of choosing 1 green disk from 3 green disks, and the number of ways of choosing 1 blue disk from 6 blue disks, and the number of ways of choosing 1 black disk from 2 black disks. So these are independent events, so we multiply them, okay? So, and all over the total number of ways of choosing 4 things from 16 things, so that would be 16 choose 4. Again, it's the same denominator as the last time. So if you multiply that out, you get 9 over 91. So the probability of picking out 4 disks, and each of the disks are a different color, is 9 over 91, okay? So the last question is, again, it's the same setup. 2 of the disks are black, okay? So what's the probability that 2 of the disks are black? So I'll just draw a line under here. 2, sorry, let's try again. Sorry, eraser's not working. So the probability that 2 of the disks are black. Okay, so the deal is that of the 4 that you pick out, 2 of them have to be black, but the other 2 can be whatever color you want. Okay, so let's concentrate on the 2 black ones for the moment. So how many different ways are there choosing 2 black disks from the 2 black disks that are there? Well, that is 2, choose 2, and the other 2 can come from any of the remaining 14. Okay, so how many different ways are there of choosing 2 things from 14 things? That's 14 choose 2. And again, they're independent events, okay? So, and then how many different ways are there of choosing 4 things from 16 things? Well, that's 16 choose 4. And then if you multiply that out in your calculator and work that out, that comes to 1 over 20. So the probability, so when you choose 4 disks, the probability of choosing 2 disks that are black is 1 over 20. All right. So that's it for the combinations there, for the probability, shall we say. So question 3 is on circle geometry. So the circle is a very big thing in the Leaving Cert course. There's only so many questions that they ask. Well, sorry, I don't mean to simplify things. There are a lot of questions that they can ask about them, but they are. I don't think they're the toughest question in the exam. Put it that way. It's their questions are generally quite long, a lot of algebra, a lot of little features, little features, aspects of the circle are under test. But generally, it's quite manageable, and there's often a lot of overlap from one circle question to the next, shall we say? All right. So what I'll do is I'll go back to my whiteboard and I'll clear the canvas. So this is question 3, okay? So the question is, the circle S, so it has a label like S, and so the equation of the circle is x squared plus y squared plus 2gx plus 2fy plus c equals 0, and that touches the y-axis at the point A, which is 0, comma minus 2. And it always helps in these, just take a look at the sketch, and again, just to identify, yes, I see A, yes, I kind of have an idea of where S is with respect to the x and y axes. And again, just to recall what the equation of a circle, or indeed any line, actually is, it is simple. It is the relationship of the x and y coordinate of every point through which it passes. So if you were to pick this point here, for example, and if you were to sub in the x and y coordinates into that point, into the equation would solve. The equation would hold, assuming you knew what g and f were. And we'll actually use that later, okay? The value of the x and y coordinate at A, i.e. 0 and minus 2, if you sub in to this equation it must hold. Okay, that's what the equation is. Okay, that's what the equation means. It's the same for lines, it's the same for parabolas, it's the same for circles. The equation is simply the relationship of all the x and y coordinates of all the point through which the circle passes. So let's go on with the question. And that's just a bit of background theory on kind of coordinate geometry in general. So part A, determine the value of f and show that c is equal to 4. Okay, so determine the value of f, so that guy there, and determine and show that the value of c is 4. So what I like about these particular questions is when he's telling you to show that something is equal to 4 or equal to an actual number, it's a sort of it's a guide in a way. Okay, he's telling you, look, the answer is 4. I want you to show me it. So at least you kind of know where you're headed. It doesn't give you the solution by any means, but it's certainly easier than, let's say, just finding the value of c, right? At least you have a target to go for. And look, if just in general, in general exam technique, when you're told to prove that something is, let's say, equal to 4, and let's say, look, that you can't quite show that it's equal to 4, but I think from there on, you're well within your rights to use the value of 4, even though you might not have proven it yourself. Okay, just keep that in mind. It mightn't work for every question, but it's certainly a good rule of thumb to have. Okay, so if I just draw out the item of interest, the diagram of interest here. Okay, no, I'm going to do a better one now than that. Sorry. There's the y-axis there. Okay, and there is the x-axis there. And I really should draw the circle first. There is a circle there. Okay, not quite a circle. And we are told that the y-axis, we are told, he does say that, doesn't he? Yes, it touches the y-axis of the point A0. So therefore we can say, look, that the y-axis is a tangent to the circle. And we can say that it is a tangent because it touches the point, that touches the circle at one point only. Okay. So in other words, the x-axis is not a tangent because, well, just by virtue of the diagram that is drawn in the question, that touches the circle at 2 points, so it's not a tangent. So the x-axis is a tangent to the circle at A. All right. Now, there's a theory. There's a theory in the course that says the radius, okay, from the center, the radius from the center of the circle is always 90 degrees to the tangent at the point of contact. Okay, so I mean, if the radius from the center of the circle is always 90 degrees to the tangent at the point of contact, then you could say so the same is true for the diameter. Okay, so therefore, the same is true for the diameter. Okay, so therefore, it's not a great diagram, but therefore the diameter, the circle, let's say that's the diameter there, and that is 90 degrees to the tangent. So therefore, the diameter must be on the line y equals -2. So all along this line, the y coordinate is -2. Okay, so that's the diameter there, and the circle is about, the center of the circle is about there. Okay, So, so that's one piece of information. The circle is on the line y equals -2. But in general, okay, we know from our course that in general, the center of a circle is -g, comma -f. Okay, right? So therefore, f equals 2, because if the y-coordinate of the center of the circle is -2, therefore f is 2. Okay, so we just put a box around that. So now the question now is, what is c? As he said, prove that c is 4. Okay, so we know, and I said before, remember that the equation of the circle is the relationship of the x and y coordinates of all the points through which it passes. The circle passes through a, which is 0, comma -2. So therefore, if we sub in 0 for x and -2 for y into the equation of the circle, we would expect the equation to hold. So recall that the equation was x squared plus y squared plus 2gx plus 2fy plus c equals 0. So what we do now is we let x equals 0 and y equals -2. Okay, and we can just sub in that. Okay, and 2fy. And we can confidently let that equal to 0 because we know that a is on the circle and it must satisfy the equation of the circle. So it's fortuitous that a number of things disappear. The 0 squareds go, -2 all to be squared is 4, plus 2g by 0 is 0, and 2f, well, we actually know the value for f, so we can write in 2 by 2, and then by the -2 there. Okay. Sorry, I forgot the plus c at the end, didn't I? Sorry. So plus c equals 0. So therefore 4 plus 2 by 2 by -2 plus c equals 0. So that's 4 minus 8 plus c equals 0. Therefore c equals 4. Okay, so we've proven that c is equal to 4. Now, of course, to do that, we would have had to find the value for f first. But importantly, I just want to get across, and I know I said it already, that since a is on this circle, we can sub it into the equation of the circle, and it will hold. Okay, that's the key theory there. So, that was the first part of the question. So, so part B, the center of S. Remember, he's referring to S as the circle. He's referring to the circle as S. The center of S lies in the third quadrant and makes a chord of length 4√3 on the x-axis. Find the value g, hence write down the equation of S. So if we were in any doubt at all, yes, the center of the circle is in the third quadrant. Okay, and we kind of knew that already. And S makes a chord of length 4√3 on the x-axis. So a chord is a point, is the line between 2 points of the circle, which is generally not the diameter. So yes, we saw before that the x-axis cuts the circle at 2 points, and the line from here to here is a chord. Okay, so what I'll do is I'll write down what we have for what we have gleaned for the equation so far, just so as we keep track of it. So it's 2gx plus 4y let's see, which I said was 4 equals 0. Right, what I'm going to do now is I'm going to just delete this part. Okay. Okay, and oh, that is old theory. So we have to find, so the center of the circle lies in the third quadrant. Center is in the third quadrant. Okay, and this chord length here is 4√3. So just by way of a revision, the quadrants are numbered anti-clockwise like that. You'll actually come up against that in a big deal in kind of the first year mechanical engineering in any university engineering course. But so we know, so we have to somehow use this chord. Okay, so we know that a perpendicular intersection from the radius that's perpendicular there. Okay, we know that that'll actually bisect a chord. That's one of our theorems. So it'll actually bisect the chord into two equal halves. And so 4√3 divided by 2 is, well, that's 2√3 there, and that's 2√3 there. Okay. So all I'm doing is just, I mean, when you see a chord, right, the first thing you're going to do really is draw a line, perpendicular line from the radius, because, you know, chord will, when you hear of a chord, you're generally not too far away from what we're doing right now. So that's our radius, okay, and it hits the chord at 90 degrees, therefore it splits the chord. And what we can actually do is we can actually complete a right angled triangle like that. So this line is 2√3. This line here is R. Okay. So we have, and we know that this line from this red marker up to this red marker is 2. Okay. Why? Because we know already that the center of the circle is on the line y equals -2. So up to the x-axis is a distance of 2 units. Okay, so we have then we have a nice Pythagoras right-angled triangle going on there. So we have 2√2, which is that guy. That's our right angle there. We have R, and we have 2. Okay, so we can say that R squared equals 2√3 all to be squared plus 2 all to be squared. Okay, therefore R squared equals 2√3 is 4 by 3, which is 12, plus 2 squared is 4. Therefore R equals 4. Okay, so the radius is 4. So that's another piece of information. I'm going to put that down in blue. Okay, sorry, it's not grade 4, but sorry about that. So now we know that as part of our circle theory, the formula for OR that relating to G, F, and C is as follows. OR is the square root of G squared plus F squared minus C. All right, that's another identity, kind of one of these general equations for a circle. Therefore, so, well, we sub in our values, because remember, we want to find G. We want to find what that is. So therefore, G squared plus F, and we said that F squared was 4. We said what F was 2, okay, and we said that C was 4. Therefore, that tumbles out 4 is the square root of G squared. Okay, so therefore, G can be -4 or +4. Okay, so, but which one is it? Okay, he said that the center was in the third quadrant. Okay, so third quadrant here. So the x coordinate of all points in the third quadrant. So the x coordinate of all points in the third quadrant is 0. Okay, and we know that sorry, it's not 0, it's negative. Sorry. Okay. And we know that the center of a circle, as before, is generally is known in a general way by minus g minus f, and we know f already. So f is we said it was 2. Okay. So therefore, so the question, to answer the question, is g negative 4 or plus 4? Well, g must be 4. Okay, in order to ensure that negative g is negative 4. Hence, the x-coordinate of all points in the third quadrant being negative. Okay, so therefore g is 4. So then we can finally fill out our completed equation now that we have found all pieces of information. So we have 2g, which is 2 times 4, which is 8x plus 4y plus 4 equals to 0. Okay, and so that's it. So the kind of key takeaways there are the use of the chord. Generally, not always, and I'm not going to put down hard and fast rules, but generally the presence of a chord will always scream some sort of bisection with the radius, and then finding out the radius by using Pythagoras. That's quite common. Okay, so that's when I did this originally, that was my first port of call, and I was able to sort it out, and then I quickly knew 2 sides of the triangle. Hence, I was able to work out the hypotenuse of the triangle, which is 4, and I was able to go from there. And so and also in these questions, there's a bit of disguising going on. The notion of the x-coordinate, the notion of the center being the third quadrant. You could have had to know then the nature of the coordinates in the third quadrant. Well, I know that the x-coordinates of all points in the third quadrant are negative, so that was able to help me with the value for g. All right. So the last part of that question, so we've written down the equation of s. That's great. The last part of that question was find the equations of the 2 tangents from the origin to s. So what I will do is I'll rub out this material. All right. And when we can take a look at those equations. All right. So now, where is the origin? The origin is here. Okay. And he says that we have to find the equations of the 2 tangents that go through the origin. Okay, so there are many tangents to the circle, but only 2 of them will go through the origin. Okay, so well, we know one of the tangents that goes through the origin, that's the y-axis. Okay, that's the y-axis there. So the first tangent is the y-axis. Okay, and the formula for the y-axis, the equation of the y-axis is x equals 0. Okay, and what about the other tangent? So the other tangent will run off like, oh sugar, no, that's supposed to hit the circle at 1 point only. Okay, that's supposed to. So the other tangent would sort of graze the circle like that. Okay, there's a intersection there. Sorry about the bad diagram. Okay, so it rests. If I could go back to the question. So it'll go from here. It'll run across the top of the circle and graze the x-axis like that. It'll be a tangent like that. Okay, that should be a straight line, but it'll be like that. So the best thing in these is just to, in order to get an equation, we have to establish, well, I think we should write down the general formula for an equation, okay, of any line. So that's y minus y1 equals m into x minus x1. x1 and y1 being the point, being the known point through which the line passes, okay? Well, x1, y1 is 0, 0. So that, because it's the origin we're talking about, so that tumbles down to y equals m into x, okay, because y1 is 0 and x1 is 0. Therefore, just to write that down in the normal form, so mx minus y equals 0. So that is the general form of the other tangent, the one I had difficulty drawing, okay? So, so what can we find out about this, okay? Well, we know that, if I just go back here, we said our circle, our point was here, okay? We know that the perpendicular distance from that center, and we know it's perpendicular distance because the line from the center of the circle to a tangent at the point of contact will make a right angle. So we're okay with saying perpendicular distance. And we know that this line here is the radius, okay? So the perpendicular distance from the center of the circle to this as yet unknown line is the radius, okay? And the point, so the perpendicular distance formula we can use, okay? So just to note what we have the center, and we went to great trouble finding that, minus 4 minus 2, and we have the radius equals 4. So we have the perpendicular distance, we have a point, and we have the format of the line. So therefore we can use the perpendicular distance formula. And just to recall the perpendicular distance formula, so ax1 plus by1 plus c all over the square root of a squared plus b squared, and that is of course the modulus of the absolute value, because we're talking about distances, and distances are always positive. So just to recall from your course what this is, a is the coefficient of the x term in the equation of the line, x1 is the x coordinate of the point of interest, b is the y coefficient, is the coefficient of the y in your equation of interest, and y1 is the y coordinate of the point of interest, and plus c then is your constant in the equation, and a and b I've already described, and or is the radius. So we can sub in our values. So a is m, okay, and x1 is minus 4, okay, and b is minus 1, because the coefficient of the y value over here is minus 1, and y1 is negative 2, and c, well, c is 0, but let's write it down anyway. And then we have the square root of, so a squared is m, and b squared is plus minus 1 all to be squared, okay? And the modulus of all that is 4, which is 4. So there's a lot of zeros here as well, not a lot of zeros. We can tidy up. So we have minus 4m plus 2. Okay, so minus 5 minus is plus. And we have the square root of m squared plus 1. All that is equal to 4. Okay, so what I could do is I could just maybe change the color here, just to bring it up here. So we have, we could square both sides to get rid of the the square root sign underneath the line. So we therefore we have minus 4m by plus 2. Let's try to write that properly. Minus 4m by plus 2 by minus 4m by plus 2 all over the square root of m squared plus 1 squared is just m squared plus 1. Okay, and all that equals to 16. Okay, and well, let's multiply this out. So minus 4m by minus 4m is 16m squared, and minus 4m by plus 2 is minus 8m, plus 2 by minus 4, or sorry, negative 4, and positive 2 by positive 2 is plus 4, and that equals 16 m squared plus 16, because I'm multiplying up by m squared. I'm multiplying up the m squared plus 1 that's underneath the line. And then we can subtract 16m squared from both sides. Then we're left with minus 16m plus 4 equals 16. Minus 16m equals 12. Therefore, m equals minus 3 over 4. So just to remind ourselves what m actually is, m was the coefficient of x that we had in the general term for the equation of this particular green line, the tangent that grazes the top of the circle and passes through the origin. Okay, so therefore the other tangent, and let's do it up here. Sorry for moving around, but so it's the other tangent, the one that goes through the origin, is negative 3 over 4 by x minus y equals 0, and multiply across by 4. No one likes fractions in these equations, so it's negative 3x plus 4y minus 4y equals 0. And we normally don't like the coefficient of the x term to be positive, so what we do is we normally don't like the coefficient of the x term to be negative, so we multiply across by minus 1. Okay, so that is the equation of the line that passes, of the other line that passes through the origin, that is a tangent to the circle. So that's one equation here, and that's the other equation. Okay. All right. So, shall we take a look at the next question? Again, this is on coordinate geometry. So 2 points, P, which is minus 4, minus 7, and Q, which is 1, minus 3, lie on opposite sides of the line 2x plus 7, 2x plus y plus 7 equals 0. Okay, so we can, again, always just appraise yourself, always just kind of just align with the diagram, just to ensure that you're happy with what the diagram is saying and that you can, it helps you to visualize it. So we have a line L kind of scooting down here, and we have the point Q here. Yes, that's in the first quadrant, and we have the point P here. Yes, that's in the third quadrant. So calculate the ratio of the shortest distances from P and Q to line L. So the shortest distances to you and me, that's the perpendicular distance. Okay, so we have the shortest distance to Q to line L, that's a perpendicular distance, and with the shortest distance from P to line L, that's a perpendicular distance there. Okay, and I'm going to explicitly draw in the presence of the right angles 90 degrees. So if I go back to my whiteboard, so we have so let's find the perpendicular distances. So P, which is minus 4, minus 7. So start, I might as well get it right at the start. So P is minus 4, minus 7. The line L is 2x plus y plus 7 equals 0. Okay, and again, I don't think it's given in the log tables. I might be wrong, but I don't think it's given. I might check that in wrong. But nevertheless, it's always good just to have that in your back pocket. Okay. I don't mean it in a literal sense. I mean it in your head. So just to fill in that formula for the perpendicular distance from line P, from point P to line L. So therefore, that's 2 times negative 4 plus 1, because that's the coefficient of the y term, and by the y1, which is negative 7, plus c, which we said was plus 7. There it is right there. And that's all over the square root of 2 squared plus 1 squared. And remember, it's the absolute value of all that because we're talking about distances. Okay, and that will tumble out to be 8 over the square root of 5. So And then in a similar way, Q is 1, 3, we said, and L is still the same as 2x plus y plus 7 equals 0. I'm not going to write out the formula again. Nevertheless, we fill in these different values. So therefore, that's 2 by 1, because the coefficient of x by the x coordinate, plus the coefficient of y by the y coordinate, plus 7 all over the square root of 2 squared plus 1 squared, and that equals 2 by 2. 2 by 1 is 2 plus 3 plus 7. That's 12 root 5. Okay, so therefore the question said calculate the ratio of the shortest distances from P and Q to line L. So the ratio, it's 8 root 5. Sorry, 8 root 5 to 12 root 5, and that equals 8 to 12, that equals 2 to 3. So the ratio of the perpendicular distances of P to L and Q to L is 2 to 3. Okay? So next part, calculate the ratio of the distances from P and Q to line L along the line PQ. So what he wants us to do now is along the line that connects P to Q, okay, along that line, which extends all the way to infinity, okay, he wants to find the ratio of these distances. So that's the point of that's the point of intersection there, right? Let's call it or, shall we say? And let's call that or. Let's call that or. So he wants to find the distance. He wants to find the ratio of P or to Q or. Okay. So, well, how do we find that? We don't even know what or is. So we have to find out what or is. And how do we find that out? Well, we have to find out the intersection of L and the line that passes through PQ. So we have to find the equation of the line that passes through PQ. Okay. So I clear that. So to find or, to find P or and or Q, we must find or, okay, and to find or, well, let's state that properly. Or is the intersection of L and the line segment PQ. Okay, so we have it. So this screams simultaneous equation. So we have to find the equation of PQ. Okay, well, this is fairly standard. So we have to find the slope of PQ first, and then sub it into the slope point formula to find the equation. So the slope of PQ okay, that equals y2 minus y1 over x2 minus x1. So we said that P was we said that P was minus 4 comma minus 7 and Q was 1 comma 3. Okay, so y2 is 3 minus negative 7 all over x2, which is 1 subtract -4. So that equals 10 plus 5, and that equals 2. Therefore, the slope of PQ is 2. So let's find the equation of PQ. Okay, so that is, we have the slope is 2, and let's use the point Q. So the reason I'm just going for Q is that's the one with positive numbers, but of course it would work out exactly the same way. So y minus y1 equals m into x minus x1. Okay, that's the point slope formula for the equation. Therefore, y minus 3 equals m, which we said was 2, by x minus 1. So therefore, that's y minus 3 multiplying your 2, 2x minus 2. Okay, and tidy that up, and you have 2x minus y plus 1 equals 0. So that is the equation of PQ. All right. So now that we found the equation of PQ, we have to find the intersection of PQ and L. Okay. So that's simultaneous equation. So we said that L was 2x plus y equals minus 7. So I'm just flipping it around slightly and bringing the 7 over to the other side of the equal sign, because I think that's more normal when solving simultaneous equations. And we have 2x minus y equals minus 1, which is the equation just found for PQ. So therefore, it's fortuitous that the coefficients of the x's are the same. So therefore, 2x minus 2x is 0. Y subtract negative y. So y minus negative y is 2y. Okay, so that's 2y there. And minus 7, just over, it's not necessary to do this rough work here, but I'll do it anyway. So negative 7 subtract negative 1. So that's negative 7 plus 1. That equals negative 6. Okay. And therefore 2y is negative 6. Therefore y equals negative 3. So if you sub your y equals negative 3 into either formula, so let's sub it into 2x equals negative 7. Therefore 2x plus 3, minus 3 equals negative 7. Therefore 2x equals negative 7 plus 3. 2x equals negative 4. X equals negative 2. So, or the name that we just made up ourselves for the point of intersection of PQ and line L, or is negative 2, negative 6. Okay, so or this point right here is negative 2, negative 6. And yes, we're kind of happy with that because both the x coordinate and the y coordinate of point or are negative, and that is the case for points in the third quadrant. So we're at least happy with the polarity of each of these two coordinates. Okay, it's always good just to appraise your work as you're going. If we got a positive value for or, we'd be a little bit worried because clearly that wouldn't be right. Okay, so we found or. Great. Sorry, that should be 3. Sorry, after all that. So or is negative 2, negative 3. Sorry about that. Okay. Because we found y is 3 there. Y is 3. So what was the next question there? So the ratio, we're still not done with that question. So let's just rub this out. So we have to find the distances from P to or and Q to or, and we have to find the ratio of those two distances, right? So we said P was negative 4, negative 7, and or, which we went to the trouble of just finding, is negative 2, negative 3. So again, well, not again, but rather, I'm sure you've used this in the past. X2 minus x1 all to be squared plus y2 minus y1 all to be squared. And that equals x2, which is, well, I just choose or as my second point. So it's -2, subtract x1, so it's subtract 4. This is subtract -4, which is adding 4 basically. Okay, and y2, which is -3, and subtract -7, so which is add negative, which is add 7. Okay, and that works out to be -2, -2 plus 4 is 2 squared, plus -3 plus 7 is 4 squared. Okay, that equals the square root of 4 plus 16. That equals the square root of 20. And that can be broken into, it's always nice to break things down, root 4 by root 5. That equals 2 by root 5. Okay, so that's the distance from P to OR. Now the distance from Q to OR, okay, so that's 1, 3 to OR, which is -2, -3. So and again, I'm using the same formula as before. So x2 minus x1 all to be squared plus y2 minus y1 all to be squared. And that equals x2. So that's -2, subtract x1, which is 1 squared, plus y2, which is -3, minus 3 squared. And that equals all that. So -2, -1 all to be squared is -3. Okay, plus -3, -3, which is -6 all to be squared. That equals 9 plus 36. That equals the square root of 45, which equals the square root of 9 by the square root of 5. That equals 3 times the square root of 5. So he said to find the ratio, let's change different color. He said to find the ratio of PR to QR. Okay, that's 2 root 5 to 3 root 5, and that's 2 is to 3. Okay, so we've succeeded in finding the ratio of this. So these aren't distances now. It's not very effective writing there. So the distance from the ratio of the distances from P to OR to Q is 2 is to 3. Okay, and we've also shown that the ratio of the distances, the ratio of the perpendicular distances from P to L to Q to L is 2 is to 3. Okay, so if I just draw out that diagram just a little more clearly. So there's your y-axis, and there's your x-axis, and there's the line L, right? And there's X, and there is P, and there is Q, okay? So the perpendicular distance from, that's L, perpendicular distance from Q to L, the perpendicular distance from P to L, okay? And we have shown that the ratio of, so these yellow figures are just ratios, right? That's 2 is to 3. These red figures are just ratios, it's 2 to 3. And then the ratio along the line connecting Q to P. Okay, this should be a straight line. That is up to this point. That's 2 is to 3. Okay, so the ratio of PR to QR is 2 is to 3. So what conclusion can you draw from your answers to parts A and B above? Explain your answer with reference to geometric theorem in your course. So just to complete. Okay, so these are so triangles triangles. Let's call this point M and this point N. So triangles QMR and PNR are similar. Okay, because their sides are in proportion. Okay, so this angle, let's draw that in green. That angle there would be equal to that angle there because they're vertically opposite. So the so I mean in the lower triangle, the side opposite, this is 2, and the side opposite, the green angle in the upper triangle is 3, and in the lower triangle, the side opposite, the 90 degrees is 2, whereas in the larger triangle, the side opposite, in terms of ratio anyway, the side opposite, the right angle is 3. So the triangles are similar. Okay. Because their sides are in proportion. Okay. So I'll go on to the next question. Question 5. 2 circles, each of radius 4 centimeters, intersect at the points C and D as shown. The distance between the centers of the circle A and B is 6 units. Okay, so this is a trigonometry, okay, and a bit of geometry thrown in as well. So find the measure of angle CAD, correct 2 decimal places. So what we've been asked to find is that angle there. Okay, that angle CAD. So if I go back to my whiteboard. So we have here so we have C, center of that is A, center of that is B, and that's D, okay? And that's shaded in there for a reason we'll see later. So he wants the measure of angle CAD. Okay, so what I would do is I would just take a single circle like that. And again, let's take the circle on the left. So we have the point A. So we have C. So that's C. That's D. And we have, so just concentrating on this, using the circle on the left, we have that, right? Because like, okay. What we've actually done is we've taken that triangle and we've done a line down through it. Okay. So we're looking at the right-hand side of this shaded area because it actually belongs to, it's within the curvature of the left-hand circle. So let's fill out some information about this. Okay. So we know that the banner there is preventing me going to the so we know that this distance is 4. Okay, we know that the distance from A to B, we know the distance from A to B is 6. So therefore the distance up to this middle line is 3 and 3 on each side. So therefore this distance up to here, that's the right angle, is 3. Okay. So again, CD could be regarded as a chord, and we've drawn a perpendicular line to it. So by symmetry, we can say that the measure of angle CAD is twice the measure of angle. We'll call that point in there. We'll call that point M. So it's twice the measure of angle CAM. Okay. So, and just so what is measure of angle CAM? Okay, so that equals so well, that's what we're looking for. Okay, but we can say that the cosine of the measure of angle CAM equals 3 over 4. So that's this angle in here. Okay, and therefore CAM, the measure of angle CAM, is the inverse cosine of 3 over 4. Okay, therefore the measure of angle CAM equals, if you were just to look up in your calculator, 41.409. Therefore, we said earlier on that the measure of angle CAD, the much larger angle, that is twice the measure of angle CAM. Therefore, the measure of angle CAD is 82.82 degrees. Okay. So the next question was, hence, it's always a sticky one insofar as we have to use the answer we just found. Find the area of the shaded region correct to 1 decimal place. Okay. So, and needless to say, is the area in this original shaded diagram. So, like I'll go over in blue here, right? So, the area. So let's call this diagram 1, and let's call this diagram 2. So the area of the shaded region in diagram 1 is twice the area of the shaded region in diagram 2. Okay, so it's a question of finding out the area of the shaded region in diagram 2. So the shaded region diagram 2 okay, so if you look at this particular diagram here, diagram 2, you can see that the shaded region is a difference between the sector CAD and the triangle CAD. So it's the so the area of the shaded region diagram, the area of the shaded region in diagram 2 is the area of the sector CAD. So the sector CAD is like the pizza slice from that large, from that circle. So it's the one with the curved edge, but we have to subtract from that the CAD triangle to get the shaded area. So area of triangle CAD. Okay, so what's the area of the sector? Well, in general, the area of the sector is the angle over 360, so whatever fraction of the overall circle that is, okay, multiplied by pi r squared being the entire area of the entire circle, and subtract the area of the triangle. So let's do this part first. We know that this particular blue, the angle I've indicated by the blue line, well, we've gone to the trouble of proving that was 82.82 all over 360, okay, by pi and the radius of this circle is 4. So that's 4 squared. Now, the area of the triangle CAD, that's, well, the area of any triangle is a half a side by the sine of the angle in between them, okay? So that equals a half by 4 by 4 by the sine of the angle in between them. And again, you see, the question said hence, so we have to use the angle that we just found, the 82.82. So we have 82.82 divided by 360 by pi by 4 squared minus a half by 4 by 4. So that equals that's 8 by the sine of 82.82. And that'll tumble out to be 7.3 square units. All right. Okay. So that is the area of this kind of crescent shaped here. So sorry, it's not. That's half of that. Okay. So the area of the diagram in diagram 2 is that's 3.65. Okay, square units. And then you must multiply that by 2 to get the area of the shaded region in the first diagram. So area of original shaded region, original shaded region. That equals 6.35 by 2, which is 7.3 square units. Okay. All right. Okay, so apologies, the writing's got a little raggedy there, but you will see that coming up a lot. The notion of kind of finding an odd shape, finding the area of an odd shape. And when I mean odd, it is like an area for which we do not have a formula. So very often you have to find the difference between two other areas for which we do have the formula. In this particular case, we had to get the area of the sector, subtract the area of the triangle because we didn't want that, and then we had to double it to get back the original shaded region. Okay. So this question here, this is a bit of a thinker, and it involves medians. Okay. This is very much a geometry question. There's no real trigonometry here. So if I just clear that. So we have, what do we have? So we have a line like that. We have up to C, down to B. Okay, and we label this as A, that's C, that's B, and then he says that in the diagram, sorry, I haven't actually drawn it out yet, I haven't actually dictated it yet. In the diagram, CD is a median of the triangle ABC. So a median is a line from a vertex to the opposite side of the triangle. And what that does, what the median does, is it splits the opposite side in two. Okay, so therefore AD equals DB. And similarly, the line, we're told here, the line segment DE is a median of the triangle ADC. So that is a line from the vertex D to the opposite side, okay, of the triangle. And again, so that implies that that side, that line segment equals to that line segment. And by virtue of CD being a median of the triangle, it means that AD equals to DB. Okay. So, so we have to show that DBC is an isosceles triangle. So in all these ones, it's good just to kind of work with the information you're given first, rather than sort of horse into the notion of the isosceles triangle. You generally have to kind of follow kind of a softly approach. Okay, and one more piece of information as well. And DE is perpendicular to AC. Okay, so it's perpendicular. So that's that. That's that. That's E, and that's D. Okay, and just to fill in the information we had last time, since DE is a median of ADC, therefore AE equals EC, and since CD is a median of the overall triangle ABC, therefore that equals that. Okay. So to show that DBC is an isosceles triangle. Okay, so therefore, so consider the measure of the angle, the triangle AED, and the triangle CED. Okay, so there's a lot of action going on here, so we might as well just write down what we know. So DE, line segment DE, is a median of triangle EDC. Therefore, we can say, and we've jotted down in the board, in the diagram already, AE is equal to EC. So I mean, I suppose the definition of a median is that it goes in the vertex to the midpoint of the opposite side. Okay, and DE is perpendicular to AC. Okay, and just to then restate another way, AED, the measure of AED equals the measure of angle CED, which equals 90 degrees. Okay, so just looking, as I say, on AED, the bottom triangle here, and CED, the triangle up and to the right of it, ED is common, is a common line. In other words, it's common to both triangles. Okay, so therefore we can say the measure, the triangle AED and the triangle CED are congruent. Okay, because congruent meaning they're exactly the same as each other, right? Because they have two lines that are equal, i.e. AE and EC are equal to each other, and ED is common to both, therefore they must be equal to each other, and the included angle, in other words, the angle in between the two equal sides, are equal, they're both 90 degrees. So that is enough to say that AED and CED are congruent triangles, okay? So then we can say that since they're congruent triangles, we can glean a bit more information. We can say that the length of AD equals the length of DC. In other words, that's the only side that's left, okay? So we can say that, we can now say that that is the case, okay? That AD is equal to DC. So, but we know that, I mean, we've already drawn it down earlier on, we know that since CD, since the line CD is a median of the overall triangle ABC, in other words, it goes from the vertex C to the midpoint of AB, then the length of AD equals the length of DB. Okay, but we've already proven that AD is equal to DC, so we can write it down there. So we can say that DC equals the length of DB. So therefore, looking at the triangle on the right-hand side, we can say that, yes, we have two sides that are the same. Therefore, the triangle DBC is isosceles. Okay, that's basically it. Okay, it's an isosceles triangle. And then if you had to go further, you could say, look, this angle then is equal to that angle, or the angles opposite the equal sides. I don't use the term base triangles in an isosceles triangle because base in English implies kind of the bottom of, but no, it's the angles opposite the equal sides. Okay. So given that the area of the triangle EDC, so this is this guy here, is 5 square units, find the area of triangle ABC. So this is a quick one, right? So we're told that the area, I'll use green ink for the areas. So we're told that ADC is 5 square units. So therefore the area of this is 5. Okay. So another aspect of the median is that when we draw a line from the median from a vertex and split the opposite side in two, the median has an effect of bisecting the area of the triangle. So since DE is a median of the triangle ADC, well then the two triangles formed, the two mini triangles formed, have the same equal area. Okay. And then similarly, since CD is a median of the overall triangle ABC, and since kind of the two triangles here, the two mini triangles on the left-hand side are 5, then this triangle must have an area of 10. Okay, so then the overall area is 5 plus 5 plus 5. It's 5 plus 5 plus 10 equals 20. Okay, so overall area. So that's a kind of a nice little feature of a median, in that it will split the area of a triangle in two. Okay, it'll bisect the area. So 20 square units is the area of the overall triangle. Okay. Okay. So that last question was a bit of a thinker, insofar as I mean, if one didn't know what the median was, one wasn't a spot of bother. So I mean, they're all aspects of the course are fair game, unfortunately. So once you did know what a median was, you know, you kind of have to break it apart. You have to write down all the information you know, all the information you can glean from what you're given, and just sort of move from there. And like, you have a target in a way. You have a target. Your target is that DBC is an isosceles triangle. Again, he's telling you that it's an isosceles triangle. You just have to prove it. So you have to know up front, well, in order to prove that it's an isosceles triangle, what do I have to say? I have to say that two sides are equal, or I have to say that two angles are equal. Okay. And, you know, we weren't really in the realm of angles there as such. We were in the realm of sides. So your best bet was to determine that two sides of the angle DBC were equal to each other. So, I mean, if you're really in doubt, kind of just start targeting it two sides at a time. And the bulk of the information provided was with respect to the, you know, the left-hand side of the figure. So chances are that one of those sides was going to be DC. Okay. So as a question then, well, do I consider CB or DB? And in the end, it was DC and DB were the sides that were the same. So I think it's in terms of an exercise of sort of inching together, inching forward slowly but surely, I think that's a very interesting question. Okay. So what I want to do is I want to move on to a question on financial mathematics. So this is a new aspect of the course, which wasn't there in my time, but it's great to see that there is an actual kind of real world application for sequence and series, which is what financial mathematics actually is. And I mean, needless to say, this part would have direct relevance at some point in life, financial mathematics. So, question 6. Padraig is 25 years old and is planning his pension. He intends to retire in 40 years' time when he is 65. First, he calculates how much he wants to have in his pension fund when he retires. Then he calculates how much he needs to invest in order to achieve this pension pot. He assumes that in the long run, money can be invested at an inflation-adjusted rate of 3%. Your answers throughout this question should therefore be based on a 3% annual growth rate. So I like the way this question breaks it down to many different parts, okay? All leading to, the part at the end. Write down the present value of a future payment of £20,000 in 1 year's time. So in other words, how much money do I have to invest right now in order to achieve €20,000 in 1 year's time, assuming an annual growth rate of 3%? Okay, so that's that's what's actually going on. So the present value of a future payment of €20,000 in 1 year's time. Okay, so the formula is future value. Future value is the present value, in other words, the money that I'd invest right now, multiplied by 1 plus I times t. So to see how the effect of this particular factor, the 1 plus I times t, that will have the effect of raising the present value to meet or to achieve the future value. Okay, so just to slot in our values, t is 1 year. Okay, that's okay. I is the growth rate, so it's 3%. So it's 3 divided by 100, and the present figure is, well, that's the one that we're looking for, and the future figure is €20,000. So sub all those figures in. €20,000 is the present value by 1 plus 3 over 100 to the power of 1. So this, I mean, needless to say, you have to use your calculator for this, and you'll find that the present value is 19,417. So if you invested €19,417 at a 3% annual growth rate for 1 year, you will have €20,000 in 1 year's time. That's basically it. So and we'll be using that sort of mindset for later in the question. So the next question is, write down in terms of t the present value of a future payment of €20,000 in t years' time. Okay, so so what this question is, if we want 20,000 years, if we want €20,000 payment in t years' time, so it's basically the exact same question as the previous one, just kept general. Okay, so as before, the future equals 20,000. Okay, and so therefore 20,000 equals whatever present figure. So that's 1 plus 3 over 100 by t. So the present figure equals, 20,000 all over 1 plus 3 by 100 by t. So if you want €20,000 in t years' time at 3% growth, you this is the formula for working out the present, the value that you must invest right now. I'm not sure the value of this particular question. It's pretty much the same as before. Anyway, Padraig wants to have this is the meat of the question. Padraig wants to have a fund that could, from the date of his retirement, give him a payment of 20,000 euro at the start of each year for 25 years. Okay, so he plans on being retired for 25 years, and he wants 20,000 euro at the start of each year, at the start of each of those 25 years. Show how to use the sum of a geometric series to calculate the value on the date of retirement of the fund required. Okay, so if I start this banner. So if I what I'm going to do is I'm going to keep that up here. So the present equals 20,000 all over 1 plus 3 to the power of 100, 3 over 100 by t. Okay, that'll be useful. That'll be useful. So if we plot out his timeline of his retirement, okay, it'll be something like this. Okay, so this is the start of year 1, and he wants 20,000 euro. I'll call that 20k. All right, and that's so at the start of the second year, he wants 20k. At the start of the third year, he wants 20k. So that all that is year 1, and this is year 2, and this is year 3. At the start of year 4, he wants another 20k, all the way up to the start of year 25, where he wants, so that's year 25, where he wants another 20k. So his pension pot, so this is the day that he retires here, okay? It's the day that he finishes work. So his pension pot on this particular day has to be able to sustain his desired income, okay? The pension pot that he's accumulated over his working life has to be able to sustain this 20,000. So different parts of that pension pot will contribute to each of these 20,000 euro. Okay, so the first 20,000 euro here, this is a future value of sorts. So the corresponding present value for that is 20,000 divided by 1 plus 0.03. Okay, to the power of 0. So it's because that present value, it's not actually, has no time to invest because he's taking 20,000 euro on the very first day of his retirement. Okay, so that present value is basically the same as the intended future value, but the next piece of money in his pension pot, that will have 1 year to accumulate in order to give him this tranche of 20,000 euro. Okay, so the present value for that is this. Okay, over 1 plus. Okay, and we're using the blue text here as our formula. And again, we worked out earlier on, this was about 19,417 euro. So we'll need 19,417 euro accumulated over this first year in order to give him 20,000 euro just at the start of the second year. Okay, and then this particular tranche of 20,000 euro, there will need to be a portion of his pension fund that will accumulate over the 2 years, okay, to make this 20,000 euro. Okay, and then finally, in order to get 20,000 euro at the start of his 25th year, okay, he'll need a present value here of 20,000 over 0.03 to the power of 24, because this particular present value will have a full 24 years to invest. And that present value will accumulate over the 20,000, will accumulate over the 24 years to give that tranche of 20,000 euro. So the pension pot that he should have on the day he retires is the sum of all these individual present values, okay? All those individual present values. All right, so there's individual present values, one present value for each of the intended future values. And the sum of the pension pot is the sum of all the present values, okay? So the question then is, well, what is the sum of all these present values? So this is a geometric series of sorts, insofar, well, it is a geometric series. We have 20,000 over 1 plus 0.03 to the power of 0. The next one is 20,000 over 1 plus 0.03 to the power of 1, and so on. Okay, so we do have, so our geometric series is, I'll just try to change the blue text here. So I'll change the blue text. So our geometric series is 20,000 all over 1 plus 0.03 to the power of 0 plus 20,000 all over 1 plus 0.03 to the power of 1 plus 20,000 all over 1 plus 0.03 to the power of 2, blah, 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 all the way up to, and when I say blah, 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 I mean like I'm just omitting all the intermediate years, but I mean they're all part of the series. It'd be too laborsome to write them all out, right? And that goes all the way up to 2 to the power of 1, so 24. So this is a sum of a geometric series, and the sum of the formula for the sum of a geometric series that equals a into 1 minus or to the power of n all over 1 minus or, okay, where a was the first term, and the first term is this guy here, so it is 20,000 all over 1 plus 0.03 all to the power of 0, okay, which is 20,000 over 1, which is just 20,000. Okay, and the geometric ratio, you know, what's one term divided by its previous term? Well, that is 1 plus 1 over 1 plus 0.03. That's or. So if you take any of these terms and divide it by its previous term, you'll get 1 over 1 plus 0.03. Okay. So we sub that into this particular formula here. Okay, so we have 20,000, okay, multiplied by 1 minus or, which we said was 1 over 1 plus 0.03, sorry, all to the power of n, and n was the number of terms, and n is 25, okay. Close that bracket there, and put that all over, and that should be a 3 there, by the way, all over 1 minus or, which is 1 minus that. Okay, so there's a lot going on here, but it's just a geometric series, and we're just subbing in the terms. We're very careful about what the first term is, i.e. a, and we're very careful about what the geometric ratio is, or, and we know that the number of terms, count them, 0 to 24, so it's 25 terms. So that will come out to be, if you work that out in your calculator, it'll come out to be 360,689, okay? 360,689. So he should have accumulated that much money in his pension pot to sustain 20,000 euro every year for 25 years. Okay, and so that's it. The next question is, Padraig plans, so now he has worked out how much should be in his pension pot on the day he retires. Now he must accumulate that, okay, throughout his working life. And that's what part D is about. Padraig plans to invest a fixed amount of money every month in order to generate the fund calculated in part C. Find, correct the 4 significant figures, the rate of interest per month that would, if paid and compounded monthly, would be equivalent to the annual rate of 3,000 euro, sorry, 3%. I'll read it again. Find, correct the 4 significant figures, the rate of interest per month that would, if paid and compounded monthly, be equivalent to the effective annual rate of 3%. Okay, so he's obviously going to be investing money on a monthly basis, probably from his pay packet or something like that. So, the formula for that is 1 plus or equals, so 1 plus or all to the 12 equals 1 plus I. And just note that this or is not the same as the geometric ratio encountered in the previous question, because or is the monthly rate of investment, where an I is the corresponding annual rate. So this is the formula that relates the monthly rate to its corresponding annual rate and vice versa. So therefore, or is the 12th root of I plus 1 minus 1. Okay, so you sub in, so it's 1 plus 3 over 100, because we said the annual rate I is 3%. So therefore, or equals 0.2466%. So what that actually means is that to have an annual rate of 3% is equivalent to having a monthly rate of 0.2466%. Okay. Part 2, write down in terms of N and P the value on the retirement date of a payment of P euro made N months before the retirement date. Okay, so do this in blue. So a payment P is made N months before the retirement date. Okay, so therefore the future value of that investment, the future value, that equals P euro by 1 plus or all to the power of N. And remember, or is the monthly rate, and N is the number of months of the investment. Okay, so so that's the formula there. So in our particular case, the future value of P euro would be 1 plus, and it's the it's that 0.2466 figure divided by 100, so it's 0.00246 all to the power of N. Okay, we don't know what N is yet. So in the next question, if Padraig makes 480 equal monthly payments of P euro from now until his retirement, what value of P will give him the fund that he retires, that he requires? So the formula for that is and it's just straight out of your course. So F equals, so he's making a contribution of P euro every month. So it's F equals P by 1 plus or by 1 plus or all to the power of 480 minus 1, okay, all over or. Okay, now from the previous question, he needs to have in his pension pot 360,689. Okay, and so how much money does it have to invest? Well, that's P euro, and the monthly rate we said was 0.00246. Okay, so these are quite computation heavy. Okay, there's no point going lightly on that, and that's 480 minus 1 all over 0.00246. So the only unknown there is P. So if you work it out, P is 392.99. So that is the amount of money that he would have to invest per month at this rate, at this monthly rate for 480 months in order to achieve the 360,689 euro. Okay. Now, part 4, if Padraig waits for 10 years before starting his pension investments, how much will he have to pay each month in order to generate the same pension fund? So it stands to reason, if he waits for 10 years, if he neglects to contribute to a pension investment for 10 years, in order to get the same amount of money at the end, he'll need to increase his monthly payments, okay, because they will have less time to accumulate, they'll have less time to grow. So a good sort of initial stab at this question is to predict that, well, the new investment, the new monthly investment amount will actually be greater than the previous one. Okay, so that'll give you an idea. So we're anticipating an answer that's going to be greater than 392.99. Okay, so if we clear the canvas, and so what's the monthly repayment now? So he doesn't have the luxury of investing over 480 months. He's actually waited for 10 years, so he's lost 10 by 12, and that is 480 minus 120. So now he has to accumulate the same pension pot, but over 360 months. Okay, so now the formula is the same as before. Okay, so it's 360,000 euro 689 equals P, and unfortunately the growth rate is still the same. Okay, that's 1 plus 0.00246 by 360 minus 1. Okay, all over 0.0. Okay, so this figure here will have a dramatic effect. It's the only one that's different to the last time. So therefore, if you work out P in this circumstance, you'll see that his monthly payments now have to increase to 623 euro 53 cents. By virtue of delaying by 10 years, he has a much bigger outlay to make, right? And that is why the Irish government are always trying to encourage people to start their pensions early in their careers, or as early as possible, because it is longer to invest until the day you retire. So if it is longer to invest, the monthly repayments, the monthly investments are a little more manageable. Okay. So that's why I like the financial mathematics part of the course, is because there's definitely a kind of a practical, real world implication or reality to it. Okay. So question 7. Okay. This is a very interesting question. This is again on trigonometry and geometry. So the diagram shows two semicircles of different radii that intersect at the point P. Okay. The larger semicircle has center O and radius 4 centimeters. The smaller semicircle has center C and radius 3 centimeters. The line through the centers OC intersects the smaller semicircle at the point S and the larger semicircle at the points Q and T. So just to read this, there's a lot going on here, right? So the diagram shows two semicircles of different radii that intersect at the point P. So that's the point P there. And the larger semicircle has center O. So the largest semicircle is the one on the left-hand side, has center O and radius 4 centimeters. The smaller semicircle is center C and radius 3 centimeters. The line through the centers OC intersects the smaller semicircle at the point S. So that's there, and the larger semicircle at the points Q and T and Q. Okay, so what are the questions? Name two triangles of equal area in the diagram and give a reason for your answer. So in these following slides, what I've done is I've just reproduced the diagram a number of times just to prevent clutter. So name two triangles of equal area in the diagram above and give a reason for your answer. So remember, a triangle, the area of a triangle is half the base by the perpendicular height. So if we want to find two triangles that have equal area, well, we should look for triangles that have the same base and the same perpendicular height. Okay, so the red triangle here and the green triangle, they have the same base. Why? The base of the first triangle is the red triangle is OT, and the base of the green triangle is OQ. Both OT and OQ are radii of the larger semicircle. Okay, so their bases are the same, and the perpendicular height from the base is the same in both cases as well. See how the perpendicular height from see how the perpendicular height of the red triangle is this line here. Okay, and that the line that I've just drawn is also the perpendicular height from the base of the green triangle. Okay, it's the same in both cases. So both these triangles have the same area. Okay. Another example of two triangles with an equal area are these ones here. Okay, these are totally different triangles, but now I'm relying upon the semicircle toward the right of the figure. Here, the red, again, in order for two triangles to have the same area, their bases should be the same and their perpendicular height from the bases should be the same. So the base of the red triangle is OC, and the base of the green triangle is CS, and both OC and CS are the radii of this smaller semicircle. Okay, their OC is equal to CS, and the perpendicular height of each of the triangles, that guy, is the same. Okay, so the perpendicular height. So that would be the perpendicular height of the red triangle, and the line that I've just drawn is also the perpendicular height of the green triangle. And again, that is the radius. So from this straight line at the bottom up to P is the same in both cases. It's the radius. It's the well, it's the same. It's not a radius. Sorry, it's not a radius, but it is the same distance nevertheless. Okay. So using the cosine rule or otherwise, show that the measure of angle, cosine of the angle OCP is 1/9. Okay, so again, just to draw in what that angle actually is. Okay, so it's the line from, so it's an angle formed from O to C up to P. Okay, so when we draw in that angle, what are the, do we have any distances at all? Can we make a triangle? We can make a triangle, yes, because from C to O is a radius of the smaller semicircle. From C to P is a radius of the smaller semicircle. and the radius of the smaller semicircle is 3, so we mark in 3 in both cases, and the line O to P is a radius of the larger semicircle, okay, and that is 4. So we have a nice triangle of sides 4, 3, and 3. So we can actually use the cosine rule and these 3 sides to find an expression for the cosine of this angle here, the one that I've indicated in red, OCP. So what that is, so the cosine of that angle is well, to apply the cosine rule to this particular triangle, we can say that OP all to be squared equals OC all to be squared plus PC to be squared minus 2 times OC by PC by the cosine of OCP. So just to go through that again, this is just the cosine rule. So the OP squared equals the sum of the other two sides squared. So that's OC squared plus PC squared minus twice those 2 sides by the cosine of the angle in between them. Okay, so therefore it's OP squared, which is 4 squared, equals 3 squared plus 3 squared minus 2 by 3 by 3 by the cosine of OCP. Okay, so that's 16 equals 9 plus 9, which is 18 minus 2 by 3 by 3. So that's minus 18 by the cosine of the measure of angle OCP. Okay, and therefore that's minus 2 equals minus 18 by the cosine of the measure of angle of OCP. Okay, therefore the cosine of the measure of angle OCP equals 2 over 18, and that's 1/9. Okay, so that explains why the cosine of OCP equals 1/9. It's an application of the cosine rule. Okay, and it's very useful in this question to draw out. I mean, in the original question, you weren't given any triangle. You have to draw it out, okay, and then see if you can apply some rule. And we were able to apply the cosine rule. So the cosine of the measure of angle OCP is 1/9. All right. So the next question was, hence show that the sine of OCP is 4√5 over 9. Okay, and when you've shown the cosine of an angle is something, you can generally work out the sine of that same angle, okay, by just applying, let's say, your corresponding, your effective or your equivalent triangle. So OCP, okay, your equivalent right angle triangle, OCP is like that, and we know that the measure of angle, we know that the cosine of the measure of angle OCP equals 1/9. Okay, so therefore this is that's the angle of interest there. So we know that this is 1, and we know that this is 9 because cosine and is adjacent over hypotenuse. So therefore we can work out with Pythagoras that this is √80. Okay, so therefore we can say that the sine of the measure of angle OCP, that equals well, the sine is opposite over hypotenuse, so that is √80 divided by 9, and that equals, well, √80, just to digress here, √80, that is √16 by √5, and that √16 is 4, therefore it's 5. So therefore that's 4 by √5 all over 9. All right, and that's proven what he wants to prove there. All right. So, he asks us another question. Find the area of the triangle OCP, giving your answer in third form. So again, we've been looking at this triangle now on a few occasions, so we have to find the area of that triangle in third form. So again, in all these long questions, a good thing to keep in mind is that when you found an answer to a question, a part, it is generally beneficial, or it's generally, a good strategy to see if you can use that straight away, because very often he isn't asking you things just for the good of his health. All the little pieces of information that you find can help with the subsequent questions. Okay, so find the error, even if he doesn't use the word hence, it is often good just to have that sort of mindset, have that sort of accumulative mindset. The outcome of one problem will help you with this solution to the next problem. So with that in mind, find the area of triangle OCP, giving your answer in third form. Okay, so we know that the area of any triangle is half of one side by another side by the sine of the angle in between them. Okay, so we know this side is 3, we know that this side is 3, and we've just gone to the trouble of proving that the sine of the OCP is 4√5/9. So to apply the formula for this particular question, we can say half by this 3 by 3 by the sine of the angle in between them. So it's the sine of OCP. Okay, that equals a half by 3 by 3, by 4√5/9. Okay, so the 3's will cancel with the 9. The 2 we'll make that 4/2. So that equals 2√5. Okay, and I think is that centimeters, I think, or square units. It's centimeters squared. Okay, centimeters squared. So that's the area of triangle OCP. Okay, so now there's another question. Calculate the areas of the two sectors OCP and POQ. Give your answer correct 2 decimal places. So I'm going to do one at a time. So calculate the areas of the two sectors OCP. So I've labeled this OCP in green. Okay, and so I'm just going to do the workings in red, just for completeness. So the area of sector OCP. So the area of the sector is generally some fraction of the overall area of a circle. Okay, so in general, it's theta over 360 by pi r squared. Pi r squared being the area of the entire circle, and in this particular case, theta is well, what is it? It's the theta is whatever angle OCP was. Okay, so that's OCP over 360 by pi r squared. But we know that the cosine, we know a lot about OCP, don't we? OCP equals a ninth. Okay, therefore OCP equals the inverse sine of a ninth. Therefore it's 83.62 measure of angle OCP. All right, so it's 83.62 all over 360 by pi, and the radius, this is a sector of the smaller semicircle, and the radius of the smaller semicircle is 3. Okay, so if you work all that out, you get 6.57 centimeters squared. Okay, so that is the area of the sector OCP. Okay, now find this area of the sector POQ. So this is a sector of the semicircle on the left hand side. Okay, the larger semicircle. So so now we have to work out, see if I can change my, I'll change the blue. Now we have to work out, oh, so sorry, I can only write in red on PowerPoint. So What is what is the measure of angle POQ? Okay, so we can see from the diagram that the measure of angle POQ equals the measure of angle POC. Okay, and we recall that if we go back to this particular diagram, okay, so we were trying to work out. So we said that the measure of angle POQ equals the measure of angle POC. They're basically the same angle there, right? But we know that in this triangle POC, the sum of the angles is 180 degrees. So therefore 180 degrees equals the measure of angle POC, which is what we want, plus the measure of angle OPC plus the measure of angle PCO. So just to reiterate, this is POC, this is the one that we want, okay? And this one, sure, and this one. So, but we know that we can tell from the diagram that POC equals OPC because they're base angles of an isosceles triangle. See the 3 and the 3 there? So that is why I drew the same symbol, this dot here and this dot here. So therefore, 180 degrees equals 2 times the measure of angle POC plus the measure of angle PCO. Okay, and therefore, just to rearrange that, the measure of angle POC equals 180 minus the measure of angle PCO all over 2. Okay, but we already know what the measure of angle PCO is. We've been doing it all along, right? If you remember, PCO is the same as OCP. Okay, it's just expressed differently. So the measure of angle PCO equals 83.62. Okay, and we had that a moment ago. There, 83.62. There it is. Here. So then, we can say that measure of angle POC equals 180 minus 83.62 all over 2, and that equals 48.18. Okay, so that is the measure of angle POC. So if I go back here, so the measure of angle POC equals 48.18. So in other words, the area of POQ equals 48.18. So therefore, I can work out the area of this sector. Okay, I can say that 48.18 all over 360 by pi by r squared, and or in this particular case, because we're looking at the semicircle on the left-hand side of the entire system, or is 4. So that's 4 all to be squared. So that equals 6.73 centimeters squared. Okay, so now we have found the areas of the 2 sectors. So that's the area of POQ, and this is the area of, so we found the area of OCP, and we have just found the area of sector POQ. Okay, so the next part is, probably should have done my workings in this particular screen, but it's not a problem. I went back to the previous diagram of the triangle anyway. So hence find the area of the shaded region correct to 1 decimal place. Okay, so the area of the shaded region. So you can tell that the area of the shaded region So again, it's a classic case. The area of the shaded region, it's a very funny shape there. So we do not have the formula for an area like that, certainly in geometry, okay? But as before, we can determine what the area of that funny shape is by getting the difference between two other shapes that we do have the area formula for. So you can say that the area that we want, so we want the area of PQS. Now we know that the area of PQS equals the area of PCS minus the area of PCQ. Okay, so just to satisfy ourselves, so the area of PCS is like that sector. Okay, that's the area. So it's a rather large. Sorry. So it's a rather large chunk of the circle. Okay, so that's the area of PCS. Subtract the area of PCQ. Subtract that guy. Okay. So if you take if you find the area of PCS and subtract the area of PCQ, you found the area of PQS. You found the gray area. So what's the area of PCS? Okay, so that's basically, as I say, is a sector of the smaller semicircle. So that is the angle of PCS all over 360, measure of angle, multiplied by pi r squared. So what is PCS? What is the measure of angle PCS? So PCS, that equals 180 degrees minus OCP. So if I go back to the previous, so you see there, PCS is that in there. Okay, it's PCS in there, but it is but OCP, this guy, on the left-hand side of that thick black line, if I add OCP and PCS, I'll get 180 degrees. But I know OCP, I've encountered that on numerous occasions, so therefore the measure of angle PCS is 180 degrees minus OCP. And I said OCP, we said OCP was 83.62. Okay, therefore the measure of angle PCS is 96.379. Okay, and that is about right, because it's just over the 90 degrees, the right angle. So we can say that the area, so therefore the area of PCS that equals 96.379 divided by 360 by pi by r squared. And r, remember, we're dealing with the smaller semicircle on the right hand side, so r is 3, so it's 3 squared. So therefore the area of PCS is 7.56 centimeters squared. Okay, so that's the area of PCS. Okay, so that's 7.56 centimeters squared. So now the area of PCQ. Okay, so the area of PCQ. Okay, the area of PCQ, that equals the area of sector POQ minus the area of the triangle OCP. Okay, so just to go back to, so what we're interested in now is that red hashed region there. Okay, that is PCQ. Okay, and how do we get that? Well, that is the sector, the pizza slice, POQ, of the larger semicircle less this triangle, okay? And we have worked out the area of POQ already, okay? We worked out the angle, the area of sector POQ was 6.73 centimeters squared. So that's 6.73 centimeters squared, less the area of triangle OCP. And we worked out that triangle OCP earlier on was 2 root 5. Okay, find the area of triangle OCP. So that's 2 root 5 centimeters squared. So less 2 root 5. And if you work that out in your calculator, you get the area of PCQ is 2.2578 centimeters squared. So that's the area of PCQ up here, less 2.2578 centimeters squared. Okay. So therefore, the area of PQS, drumroll, the area of PQS, the area of the dark shaded region there, is 7.56 centimeters squared minus 2.2578 centimeters squared, and that is equal to, so area of PQS is 5.3 centimeters squared. Okay. So there's a lot going on there. I would encourage you to go back through the YouTube video and just maybe at the end of each step, pause and assimilate what I've done. Okay, it's all written down, admittedly a little scraggly, but I've done it in the right order. Okay. So the area of PQS is 5.3 centimeters squared. The reason why I like this question is that there is so much going on. There's so much interlocking and interrelated concepts, interrelated angles, and so on, that it really benefits kind of a repeated viewing. And when I was doing this first, it didn't come across easy. It didn't come across as easy as I'm making it right now. But I've done this a number of times. But I think the value of this particular sum is actually quite significant. There's a lot going on here. It does check a lot of individual things. And I think once you have a question of this complexity down, I would say that your kind of geometry and trigonometry is very strong. All right. So that's why I like the question. It's not over though. Find the perimeter of the shaded region correct to one decimal place. So the perimeter of the shaded region is all that line plus that line plus that line. Okay. So this is the last question, by the way. So so what we're looking for, we'll do it in terms of arc PQ plus arc PS plus QS. Okay. So let's do it one at a time. So therefore arc PQ. So this is the arc, this is part of the circle. Okay. So it's like it's the edge of that sector POQ of the larger semicircle. So that, well, you know that it's some ratio, okay, of the overall circle, and this it's some fraction of the circle, some fraction of the circumference. The circumference in the case of the larger circle being 2 pi r. So and we know the measure of angle POQ is 48.19. And where did we get that earlier on? We got that 48.19. That was the inverse cosine of yes, that was the POQ here. We got the POQ there. All right. and we said the POC was, yes, we said down here the POC was 48.18. 48.19, same thing. All right, so if I go back here, so 48.189 over 360, okay, by 2 pi r, that equals 3.36 centimeters. Okay, so we know that guy. And then arc PS. So this is an arc now of the smaller semicircle. So so it's like the length of the arc with PCS as its center. So that's the angle PCS over 360 by 2 pi by 3. Okay, and we said the PCS earlier on was a 96.379. Okay, so that's 96.379 divided by 360 by 2 pi by 3, which is 5.04. It's a 5.04. Therefore, we know that guy. So then QS, so it's the very last thing. So QS, the length of QS, that is OS. That's the diameter of the smaller semicircle minus OQ. Okay. And so it's OS is twice the radius of the smaller semicircle less OQ, which is the radius of the larger semicircle. So that's 4. So therefore that's 3 times 2, which is 6 minus 4, which is 2. So therefore we have that guy. So we have the 3.36 for arc PQ. We have 5.04 for arc PS, and we have 2 for the straight line QS. So add them all up together, and we have the grand total of 10.4 centimeters. So the reason why, as I say, I like this particular question, there's so much going on in it, and it is, PQS, the shape of it looks awful, the area of it looks terrible, and the outline of it looks very intimidating. But it's fascinating how you can break it down, and you can just use the notion of sectors, use the notion of triangles to pick off the relevant details of it. So I strongly encourage you to go back through this recording and just go through it step by step yourself, and just to see the accumulating nature of this particular question. That's why I like it. This is a particularly long question. I'd be astonished if something as lengthy as this came up in the Leaving Cert. I really would. This would be regarded as a challenging question. But I of course, I'm open to correction. There are always surprises. But I think once you nail this, and once you're happy with the method here, and it'll force you to go back and check things and recheck things in your book. I think it's a very rewarding question to go through. Okay.
Essentially, I want to say, on behalf of the CIA, I want to say thank you to Paul and all of the tutors that have given up their time to take several topics, in some cases, from the Leaving Cert Maths curriculum, and give you their take, including solving several exam questions from past papers. So thank you, Paul. Also, thanks to Edmund Collins, Jerry Sweeney, Mark Murphy, Deirdre DeValuche, Adrian Williams, Frank O'Keefe, John Forrest, and Suzanne O'Callaghan, who you met earlier today also. So for now, I think that's all. I don't see any questions coming in. So thank you, Paul, and all the tutors for all your time again this year.